Imagine the edge of our solar system. It's so far away that even light needs more than 17 hours just to reach it. And beyond that edge, in a darkness so cold that nitrogen freezes into sheets of ice, entire worlds are orbiting our sun, completely unseen. Not small fragments, not debris, worlds, some larger than anything in the asteroid belt. And in 2025, one of them revealed something no one was prepared for. Not a signal, but a pattern, etched into its frozen surface, written in chemistry, waiting for billions of years to be read. The James Webb Space Telescope finally saw it, and what it found didn't just add a new discovery. It quietly challenged everything we thought we understood about the outer solar system and what might still be hiding within it. The discovery announcement came in the form of a preprint, which is how most genuinely surprising things in planetary science arrive. Not with a press conference, not with a prepared statement. With a document uploaded to a public server at 3 a.m, author affiliations listed, methodology explained in fine print, conclusion buried in section 7. The object was designated 2017 OF201. The year in its name tells you when the archival images that captured it were taken, not when it was found. It was found in 2025. Nobody was looking for it specifically. It emerged from a systematic pass through decades of archived telescope data. It's a computational sieve designed to catch things that move against the fixed stars at the precise rates consistent with extremely distant solar system objects. The team that found it did not immediately understand what they had. The first pass through the data flagged it as an anomaly. The second pass confirmed the anomaly. The third pass began to build an orbital solution, and the orbital solution was the moment the room went quiet. 2017 OF201, already being called OFI in informal communications, is approximately 430 miles across. That makes it larger than many named asteroids, larger than several of the moons of the outer planets, and firmly in the category of objects that planetary scientists classify as likely dwarf planets. Its surface, based on the limited spectroscopic data available at the time of discovery, appeared reddish in a way consistent with organic compounds processed by billions of years of cosmic radiation. At the moment of its discovery, it was sitting at roughly 90 astronomical units from the Sun. An astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. 90 of those units is a distance that resists normal intuition. Hold the rock again. The distance from Earth to the Sun, if you walked it at a normal human pace without stopping, would take more than 3,000 years. OFI was sitting 90 times that far from us, but the distance at discovery was almost beside the point, because what the orbital solution revealed was not where OFI was. It was where OFI goes. At its closest approach to the Sun, the object swings into approximately 45 astronomical units, at a distance comparable to the orbit of Pluto on a typical day. At its farthest, the orbit extends outward to approximately 1,600 astronomical units, a distance so extreme that it places OFI in a region of space called the inner Oort cloud, a region theorized for decades but barely explored, barely mapped, barely understood. The orbital period required for a single trip around the Sun at that scale is somewhere in the vicinity of 25,000 years. 25,000 years. When OFI last occupied the position it is in right now, the most recent ice age was not yet finished. Humans were painting horses and aurochs on cave walls in what is now southern France. The pyramids were not built. Writing was not invented. Cities did not exist. And this object was somewhere else entirely in its circuit of the Sun, visible from the cold, dark outer reaches of the solar system, invisible to every eye on Earth because no eye on Earth would have known to look. The discovery alone would have been enough for a significant paper. A new distant dwarf planet candidate with an extraordinary orbit, found hiding in archival data, unknown for 8 years despite sitting in plain sight in the records. That would have been the story. But the orbital solution produced by the team created a problem that was more interesting and more urgent than the discovery itself. The problem was Planet 9. In January 2016, two planetary scientists at the California Institute of Technology published a paper that immediately became one of the most discussed and most contested documents in modern astronomy. Konstantin Batygin and Mike Brown were not unknown figures. Brown was already famous within the field for his work on distant solar system objects, particularly for the discovery of Eris, the large distant object whose existence had triggered the reclassification of Pluto as a dwarf planet in 2006. Brown had been responsible, in a sense, for demoting Pluto, a fact that earned him the nickname Mike Brown Planet Killer in the popular press, and a level of notoriety unusual for a researcher who works primarily on things nobody can see without a very large telescope. The 2016 paper was not a discovery. It was an argument. The argument went as follows. In the outer solar system, beyond the orbit of Neptune, at approximately 30 astronomical units, there exists a population of icy bodies collectively called trans-Neptunian objects, or TNOs. Most of them cluster relatively close to the plane of the solar system and orbit in well-understood patterns. But a subset of these objects, the ones with extremely elongated orbits that reach out to hundreds of astronomical units, the extreme trans-Neptunian objects, or ETNOs, showed something odd. Their orbits, when examined carefully, were not randomly distributed. They were clustered. Specifically, the elongated, distant parts of their orbits were pointing in similar directions, and the orbits themselves were tilted in correlated ways. The probability of this clustering occurring by chance, Batygin and Brown calculated, was approximately 1 in 15,000. Something was organizing those orbits. Something massive and distant was exerting gravitational influence on this population of objects, shepherding them into alignment the way a large hand pressing through sand leaves a pattern in the grains around it. Batygin and Brown proposed the simplest explanation consistent with the data. A planet. A planet somewhere between 5 and 10 times the mass of Earth, orbiting the Sun at a distance of several hundred astronomical units, completing one orbit every 10,000 to 20,000 years, currently positioned somewhere in the sky where no telescope had yet happened to look. They called it Planet 9, because the solar system had previously been considered to have 9 planets before Pluto's demotion, and the hypothetical new object would restore the count to 9 if confirmed. The scientific community's reaction was immediate and split almost perfectly down the middle. At one half found the clustering evidence compelling and the hypothetical planet plausible. Brown and Batygin's calculation was careful. The orbital bias they identified was real in the data. And the existence of an undiscovered massive planet in the outer solar system was not inherently absurd. Neptune itself had been discovered in exactly this way in 1846. Its position predicted mathematically from the unexplained perturbations in the orbit of Uranus, before anyone had ever pointed a telescope at the right patch of sky. The logic was respectable. The history was reassuring. The other half was unconvinced and said so loudly. The skeptics had several arguments. The first was selection bias. The ETNOs, whose orbits showed the suspicious clustering, were not a random sample of the outer solar system population. And they were the ETNOs that had been discovered, and discovery required that an object pass close enough to the inner solar system to be detectable with existing instruments. That selection criterion might itself introduce a bias in apparent orbital alignment that had nothing to do with a perturbing planet. If you can only see objects that pass through a certain region of space, the orbits of the objects you find will share properties related to passing through that region, even if no organizing planet exists. The second argument was the absence of detection. Surveys of the outer solar system had been ongoing for years. The sky had been mapped, catalogued, remapped. Something 5 to 10 Earth masses in the outer solar system should be detectable even at those distances with sufficiently sensitive surveys. The surveys had found nothing. And the third argument was that alternative explanations existed for the orbital clustering, explanations that did not require an undiscovered planet. The gravitational influence of the Milky Way itself, the so-called galactic tide, can affect the orbits of distant solar system objects. Stars passing near the solar system during its early history could have scattered and tilted orbits into unusual configurations. The early chaos of solar system formation, when the giant planets were migrating inward and outward and scattering debris in every direction could have left statistical fingerprints that look like clustering without any current organizing body. For 9 years, from 2016 to 2025, this debate continued without resolution. New ETNOs were found, some consistent with the Planet 9 prediction and some not. Surveys searching for the planet directly found nothing, which was either evidence against its existence or evidence that it was simply in a part of the sky not yet searched with sufficient depth. The hypothesis persisted in a state of productive uncertainty, not confirmed, not refuted, still generating papers, still drawing researchers, still occupying the conversation at every outer solar system conference. Then Ophi arrived, and the conversation changed. The problem with Ophi is not its existence. Objects at extreme distances in elongated orbits are, in principle, consistent with Planet 9. The problem is its specific orbit, its specific orientation, and what that orientation means for the mechanism that Planet 9 is supposed to create. The Planet 9 hypothesis requires that the hypothetical planet be shepherding distant objects into correlated orbital alignments through gravitational interactions over long time scales. The mechanism is well understood mathematically. Repeated gravitational nudges from a massive body can produce a coherent pattern in the orbits of smaller objects, even objects that never come close to the planet itself. This is not controversial physics. It is the same mechanism responsible for the gaps in Saturn's rings, for the clustering of asteroids in certain orbital resonances with Jupiter, for dozens of observed patterns in the solar system. The physics is solid. What the physics requires, however, is that the objects showing correlated clustering actually be subject to the planet's gravitational influence, and an object that spends almost all of its time far outside the region where Planet 9's gravity is significant should not show the clustering signature. And this is the problem. Ophi's orbital properties do not match the clustering that Planet 9 would produce. Its orbital orientation is different from what the hypothesis predicts. Its orbital inclination is different. It behaves, in the data, as if Planet 9 either does not exist or is not where the current models place it. The team that discovered Ophi noted this explicitly in their paper, carefully and without drama, which is how planetary scientists deliver bad news. And they noted that the orbital parameters of 2017 OF201 are inconsistent with the dynamical predictions of the Planet 9 hypothesis, and that its discovery adds to a growing body of evidence that the orbital clustering of ETNOs may require reinterpretation. This was not a declaration that Planet 9 does not exist. Science does not work that way. One object cannot single-handedly falsify a hypothesis as complex as Planet 9, because the hypothesis makes statistical predictions about populations of objects, and populations cannot be judged from a single data point. What Ophi did was different and more subtle. It widened the statistical uncertainty. It demonstrated that the outer solar system contains objects that were not anticipated by the Planet 9 framework, and that the population being used to support the hypothesis may be less clean, less correlated, and less definitively organized than the original 2016 analysis suggested. Badigan acknowledged this in a public statement that was characteristically direct: the discovery of objects that do not fit. The predicted clustering does not kill the hypothesis, but it requires the hypothesis to evolve. More data was needed. A more complete census of the outer solar system was required before any conclusion could be drawn. The Vera Rubin Observatory, scheduled to begin its legacy survey of space and time in the mid-2020s, would provide that census eventually. Until then, the debate would continue. And that was where things stood when James Webb turned toward the Kuiper Belt. The James Webb Space Telescope was designed for deep time and deep space. Its primary mission was the early universe, the first galaxies, the light that left its sources before the Milky Way existed. The outer solar system was not its original focus, but the instrument's capabilities, its extraordinary sensitivity in the infrared, its ability to resolve spectroscopic detail that no previous space telescope could match, made it uniquely suited to something that planetary scientists had been requesting for years. Solar system objects are cold. The surfaces of bodies in the outer solar system are at temperatures ranging from roughly 40 to 70 degrees Kelvin, which is between -388 and -333 degrees Fahrenheit. At those temperatures, objects emit almost nothing in visible light and reflect only a fraction of the already faint sunlight reaching them. But in the infrared, they glow faintly with their own thermal emission, and the compounds on their surfaces leave precise, spectroscopic fingerprints that an instrument like Webb can read. The surfaces of Kuiper Belt objects and beyond are chemical libraries. Billions of years of solar radiation processing, cosmic ray bombardment, and slow geological activity have turned their icy surfaces into complex mixtures of organic compounds, frozen nitrogen, frozen methane, frozen carbon monoxide, water ice, and a dark reddish material called tholin, which is produced when simple organic molecules are irradiated over long time scales. The specific mixture on any given object tells you something about where it formed, but what conditions it experienced during the early solar system, and how it has changed over time. Nobody had been able to read those libraries in detail before Webb. Previous instruments could identify broad spectral features, the presence of water ice or methane, yes, but the fine structure of the spectrum, the precise ratios of different compounds, the subtle signatures that distinguish one formation environment from another, those details were lost in the noise. Webb changed that. Webb has a primary mirror 6.5 meters in diameter, cooled to within a few degrees of absolute zero, equipped with spectrographs sensitive enough to measure the chemical composition of an atmosphere 200 light-years away. Pointed at a frozen body 50 astronomical units from Earth, it becomes something unprecedented in the history of solar system science. Sean, it becomes a reader of frozen messages. This is not a metaphor. The chemistry preserved on the surface of a Kuiper Belt object is a record. It is a record of temperature during solar system formation, of the radiation environment at different epochs, of collisions and resurfacing events, of the object's own interior processes. The record is imperfect and incomplete, but it is a record. And the spectroscopic data Webb returns, if interpreted carefully, is a kind of reading. In 2024, a team led by researchers at the Southwest Research Institute began designing a systematic Webb observation program targeting a carefully selected sample of Kuiper Belt objects and beyond. The program was called Architects, an acronym that pleased nobody but persisted anyway. The stated goal was to build the first comprehensive spectroscopic library of distant solar system objects using Webb's near-infrared and mid-infrared instruments, covering the compositional range from classical Kuiper Belt objects in near-circular orbits close to 40 astronomical units all the way out to the most distant ETNOs and any new objects discovered in the meanwhile. The program was designed before Ophi was found. When Ophi was found, it was added to the target list. Webb was pointed at Ophi in September 2025. The results arrived in November, and they stopped the team cold. The spectrum of 2017 OF201 is, in the language of planetary scientists, unusual. In the language of the broader scientific community, it is deeply strange. In the language of this investigation, it is the thing that forced a rethinking of an entire chapter of solar system history. A spectrum is a barcode. Every atom and molecule absorbs and emits light at precise, characteristic wavelengths. And when you spread the light from an object across its constituent wavelengths, the dark absorption lines and bright emission features that result are as specific as fingerprints. No two compounds produce exactly the same spectral pattern. A skilled spectroscopist looking at a well-resolved spectrum can identify individual molecules the way a reader recognizes words. Ophi's spectrum showed what the team expected to find: water ice, the reddish tholins consistent with long-term radiation processing, carbon dioxide features, and traces of carbon monoxide. These are the standard ingredients of outer solar system objects. If they are the baseline, they are the background noise against which anything interesting stands out. What stood out was a compound that should not have been there. The precise nature of the anomalous compound remained under analysis as of the initial report, but the spectral signature was consistent with a class of complex organics that form under specific temperature and radiation conditions not typical of where Ophi currently orbits. More precisely, the compounds appeared to have formed at temperatures and radiation intensities higher than what Ophi experiences at its current distance. The object's surface was carrying a chemical record from somewhere else, somewhere warmer, somewhere more energetically active. This was not, on its face, impossible. Objects in the outer solar system move. Ophi's orbit takes it from 45 to 1,600 astronomical units in a single sweep. At 45 astronomical units, it is close enough to the Sun that its surface experiences significantly more radiation than at its current 90 astronomical unit position. A surface compound formed at perihelion, the closest approach to the Sun, could survive for millions of years as the object retreats to greater distances. The temperature modeling was where the story became more specific and more uncomfortable. The team calculated the expected surface temperatures at various points in Ophi's orbit and matched those temperatures to the formation conditions for the observed compound class. The result was not consistent with formation at 45 astronomical units. The compounds required conditions closer to 30 to 35 astronomical units, that is inside Neptune's orbit. Not dramatically inside, but meaningfully inside. It is a region of the solar system where no stable orbit for a 430-mile object currently exists. Neptune's gravity would perturb any object at that distance into either a different orbit or out of the solar system entirely within a relatively short time. The implication was not comfortable. Ophi's surface chemistry suggested that the object had spent time, possibly a long time, in a region of the solar system it could not currently occupy. It had been somewhere it no longer was. Its surface was a record of a previous life. The team had a word for this: paleogeochemistry, the chemistry of ancient environments preserved in frozen form. And what the paleogeochemistry of Ophi was suggesting, very cautiously with every appropriate caveat attached, was that the outer solar system of today is not the outer solar system of the past. Something had changed. Objects had moved. The architecture had been different. This is where the Kuiper Belt itself entered the story, and where the 1,000-year timeline that gives this investigation its title first appeared. You could fit the entire asteroid belt, all of it, every rock and rubble pile between Mars and Jupiter, into a ball roughly 4% the mass of the Moon. The Kuiper Belt makes the asteroid belt look like a footnote, stretching from roughly 30 astronomical units, where Neptune orbits, to approximately 50 astronomical units. It contains an estimated 100,000 objects larger than 100 kilometers in diameter and trillions of smaller pieces. Pluto is in the Kuiper Belt. Eris, the object that dethroned Pluto, is in the scattered disk that borders the Kuiper Belt. Makemake, Haumea, Quaoar, Sedna, all the named dwarf planets of the outer solar system, are Kuiper Belt objects or closely related relatives. The Kuiper Belt is not an accident, it is a fossil. It is the debris left behind after the solar system's 4 giant planets formed and migrated, scattering the original disk of planetesimals that extended beyond Neptune into the configuration we see today. The NICE model, named for the city in France where it was developed, describes this process in broad strokes. In the early solar system, Jupiter, Saturn, Uranus, and Neptune formed in a more compact configuration, then began migrating outward as they exchanged orbital energy with the disk of smaller objects around them. Neptune, in particular, migrated significantly outward, scattering objects into the Kuiper Belt, the scattered disk, and the region of extremely distant orbits that eventually become the inner Oort cloud. The objects we find in these regions today are the survivors of that scattering event, the ones that ended up in stable niches rather than being ejected from the solar system entirely. This history has consequences for what those objects look like chemically. Objects that formed close to Neptune, at roughly 20 to 30 astronomical units, in a region where temperatures were relatively higher and radiation environments were more intense, would have different surface chemistry than objects that formed in the colder, more distant regions of the protoplanetary disk. The chemical signatures on their surfaces are records of where they formed, not where they ended up, and this is the key. Now, the surfaces of Kuiper Belt objects are, in a very real sense, time capsules. They preserve information about conditions in the early solar system that no longer exist anywhere in the solar system today. They are billion-year-old frozen records of a configuration that ended before Earth's oceans formed. But there is a complication, and the complication is cosmic radiation. The surface of an outer solar system object is not a perfectly sealed record. It is constantly being processed. Galactic cosmic rays, the high-energy particles produced by supernovae and accelerated across the galaxy, bombard the surfaces of Kuiper Belt objects continuously and penetrate to depths of meters, gradually converting simple molecules into complex organic polymers, darkening surfaces, and erasing the uppermost chemical layers over time. The reddish tholins visible on many outer solar system objects are the product of this long radiation processing. A fresh surface, like one exposed by a collision or a geological resurfacing event, would look different, brighter, with a different spectral character. This is where the 1,000-year timeline enters, and where the word message becomes, not metaphor, but a specific technical description. A paper published in the journal Icarus in early 2025, several months before the Webb observations of Ophi, had modeled the radiation processing rates for surfaces of outer solar system objects at various distances from the Sun. The modeling was careful and took into account the specific flux rates for different types of cosmic radiation, the depth dependence of different chemical transformations, and the thermal cycling that outer solar system surfaces experience over their orbits. The conclusion of that modeling was expressed in units of years. The characteristic timescale over which cosmic radiation erases and overwrites surface chemistry at the depths Webb can probe is approximately 1,000 years. 1,000 years. This means that the spectral fingerprint Webb reads on the surface of an outer solar system object is not a record of its entire 4.5 billion year history. It is a record of the last 1,000 years. The surface is being continuously rewritten. The record Webb reads was written in the cosmic ray sense, in the last millennium. What was there before, what the object looked like 1,000,000 years ago or 100 million years ago, has been erased and replaced by whatever conditions the object has experienced in the last 1,000 years of its orbit. When the team analyzing Ophi's Webb spectrum understood this, the anomalous compounds on its surface took on a different character. If the surface record represents only the last 1,000 years, and the compounds present require formation conditions warmer than Ophi's current orbit allows, then either the formation conditions changed significantly within the last 1,000 years, or the anomalous compounds survived from a period of surface activity, a geological event, a collision, a resurfacing, something that exposed fresh material from the interior, where older chemistry from the object's formation environment might still be preserved. The second option was what the team found most plausible, and the type of resurfacing event most consistent with the spectral pattern, with the specific compound classes present and absent, with the distribution across the visible surface, was a collision. Something had hit Ophi, not recently by human standards, somewhere within the last 1,000 years, by cosmic ray clock standards, which means anywhere from 1 year ago to 1,000 years ago on a human calendar. A collision had exposed fresh material from the interior, and that fresh material contained chemistry from deep inside the object, chemistry that formed when the object was somewhere warmer, somewhere with a different radiation environment, somewhere it no longer orbits. The surface of Ophi was a message in the technical sense, a message written by an impact event sometime in the last millennium, readable because Webb could decode its chemistry, interpretable because the cosmic ray clock told you when the writing happened. A 1,000-year-old message from the interior of a world that formed before Earth's oceans existed, sitting in the frozen outer solar system, waiting for an instrument powerful enough to notice it. That was the discovery. That was what the headlines meant, even when the headlines oversimplified it. That was what stopped the team cold. But the deeper question was not what the message said. The deeper question was what it implied about where Ophi came from. And that question leads into one of the most active, most uncertain, and most fascinating debates in planetary science. Before we can understand what Ophi is, we need to understand what a planet is. This sounds like a philosophical digression, but it is not. Yet the definition of what counts as a planet shapes which objects get studied closely, which get ignored, which get funding, which get named, and which get left in databases as alphanumeric strings that nobody can pronounce. The definition matters. The International Astronomical Union, the body responsible for these classifications, uses 3 criteria for full planetary status. An object must orbit the Sun. It must be massive enough that its own gravity has pulled it into a roughly spherical shape, the condition called hydrostatic equilibrium. And it must have cleared the neighborhood around its orbit of other debris, establishing itself as the dominant gravitational presence in its orbital zone. The third criterion is the one that caused trouble in 2006. Pluto orbits in the Kuiper Belt. Surrounded by thousands of other objects in similar orbits, it has not cleared its neighborhood. It coexists with a large population of comparable bodies. This makes it, technically, a dwarf planet, which sounds like a diminutive but is actually a separate classification entirely, not a smaller version of a real planet but a different category of object. Ophi almost certainly cannot clear its orbit. Its orbit is so elongated, so extreme, that it spends most of its time in regions of space where it would encounter a completely different population of objects at perihelion versus aphelion. It cannot gravitationally dominate a neighborhood it visits only transiently. It is a dwarf planet candidate. But the definition question becomes genuinely complicated in the outer solar system for a reason that the IAU did not fully anticipate in 2006. Yes, the clearing criterion was designed around the inner solar system, where planets have had 4.5 billion years to gravitationally organize their neighborhoods. In the outer solar system, at distances of hundreds of astronomical units, the timescales for gravitational clearing are longer than the age of the solar system itself. An object at 500 astronomical units orbiting the Sun at the measured orbital velocity for that distance takes tens of thousands of years just to complete one orbit. It cannot possibly clear anything in the time the solar system has existed. This means that the IAU's definition, applied literally, would classify almost any object at extreme distances as a non-planet, regardless of its mass. A Mars-sized body at 500 astronomical units would be a dwarf planet by this criterion. And an Earth-sized body at 800 astronomical units would be a dwarf planet. Conceivably, even a body the mass of Neptune, if placed far enough from the Sun, would fail the clearing criterion. This is one of the reasons the Planet 9 debate is so philosophically interesting. If Planet 9 exists and has a mass 5 to 10 times Earth's, it might or might not satisfy the clearing criterion depending on how you define its neighborhood. At its hypothetical distance, the concept of a cleared orbital neighborhood becomes almost meaningless. Ophi sits somewhere in the middle of this definitional gray zone. At 430 miles in diameter, it is certainly not massive enough to clear any orbit, but it is potentially large enough to be in hydrostatic equilibrium, which would make it a dwarf planet in the formal sense. And the team that discovered it used the term likely dwarf planet candidate, and then spent the next several months resisting pressure to apply the word dwarf planet definitively until more data on its shape and density becomes available. This definitional wrestling matters for the Webb story, because the chemical record Webb can read depends on what kind of object is being examined. A body large enough to have experienced internal heating, perhaps from the decay of radioactive isotopes in its rocky core, would have a different interior chemistry than a smaller body that froze solid and stayed frozen. The compounds preserved in Ophi's interior, the ones exposed by the impact event that the Webb data appears to record, are consistent with a body large enough to have had a differentiated interior, a rocky core and an icy mantle, the kind of layered structure that requires enough mass for gravity to sort materials by density. This is not a small detail. It means Ophi is not just a random icy body. It is potentially a geologically complex world that formed in a specific environment, spent time in a different environment, was struck by something large enough to expose its interior chemistry, and has been sitting in the outer solar system ever since, carrying the record of its history on its frozen surface. waiting for James Webb. To understand why Ophio's surface chemistry implies it formed somewhere warmer than where it orbits now, you need to understand the architecture of the early solar system, and specifically what changed. The story of how our solar system reached its current configuration is a story of migration, violence, and surviving chaos. At 4.5 billion years ago, the Sun was surrounded by a protoplanetary disk, a rotating pancake of gas and dust stretching from the inner solar system to distances of perhaps 100 astronomical units. In the inner disk, rocky planets grew from the aggregation of silicate and metal-rich materials. In the outer disk, beyond the snow line, the point where water freezes, the material was richer in volatile ices, and the objects that formed there were both larger and more numerous. Jupiter formed first, and its formation changed everything. A body the mass of Jupiter forming in the outer disk was gravitationally disruptive on an enormous scale. Its growth absorbed and scattered material in its vicinity, and as it accumulated mass, its gravitational influence extended further and further outward. Saturn formed shortly after Jupiter, and then the two giant planets entered into an orbital resonance, a gravitational dance where their orbital periods were related by simple integer ratios, and that resonance drove both planets to migrate. Jupiter moved slightly inward, Saturn moved outward. Uranus and Neptune, forming in the same period, were scattered by these migrations into orbits that put them on a collision course, in the gravitational sense, with the outer disk. The NICE model describes what happened next as a relatively late instability, possibly occurring as recently as 700 million years after the solar system formed. In this model, Uranus and Neptune migrated rapidly outward, sweeping through the Kuiper Belt precursor and scattering its objects in every direction. Some were thrown into the inner solar system, producing the period of intense bombardment recorded in lunar and Earth craters. Some were thrown outward into the Oort cloud, some ended up in the scattered disk, and some settled into the Kuiper Belt's current configuration, trapped in gravitational resonances with Neptune's new position. For Ophio's surface chemistry to make sense, what matters is a specific detail of this migration story. During the NICE model's instability, there was a period when Neptune was in an orbit between roughly 20 and 30 astronomical units, closer to the Sun than its current 30 astronomical units, sweeping through the disk and scattering objects. An object that formed in the disk at 25 to 30 astronomical units in the warmer, more radiation-intense inner Kuiper Belt precursor would have acquired a surface chemistry consistent with those conditions. If that object was subsequently scattered to a more distant orbit by Neptune's migration, it would carry that chemistry to its new home. Ophio's surface appears to be telling exactly this story. The anomalous compounds visible in the Webb spectrum, the ones requiring warmer formation conditions, are consistent with an origin at 25 to 30 astronomical units during the period of Neptune's migration. What Ophio's interior may preserve, exposed by the impact event, is a chemical record from a solar system that looked different from the one we inhabit now. This is not a revolutionary conclusion in isolation. Planetary scientists have long believed that many Kuiper Belt objects were scattered outward from closer in-formation sites. What makes the Webb data valuable is that it provides the first direct spectroscopic evidence for this kind of chemical signature in a specific object at this particular distance. It is the difference between knowing in theory that objects were scattered and reading the chemical record of that scattering on an actual surface. But the chemical record on Ophio's surface is not just speaking about Neptune's migration. It may be speaking about something further out, something larger, something that is still, possibly, out there. The orbit of 2017 OF201 is a geometric record as surely as its surface is a chemical one. The specific parameters of that orbit, the eccentricity, the inclination, the orientation of the elongated axis, the perihelion distance, all of these are consequences of the gravitational history that produced the orbit. You cannot have an orbit without causes, and the causes leave fingerprints in the orbital parameters. The question the team turned to after the Webb surface analysis was whether the orbital parameters of Ophio could be fully explained by known gravitational influences, or whether they required something additional. The known influences are Neptune, the other giant planets, the galactic tide, and the occasional passing star. These can be modeled. Their effects on test particle orbits in the outer solar system have been studied extensively, and the predictions are well established. Running Ophio's orbit backward through time, using the best available models for the gravitational environment of the outer solar system, produces a trajectory history. Start with the current orbit. Apply the gravitational forces from all known sources. Run the clock backward in increments. Watch where the orbit came from. The result, expressed in the team's paper with appropriate cautionary language, was that the known gravitational influences do not fully account for Ophio's current orbital configuration. The orbit can be produced approximately by gravitational scattering from Neptune in the context of the NACE model's migration history. But the specific inclination and orbital orientation of Ophio, when compared to the predicted distribution of scattered disk objects under Neptune's influence alone, sits in a region of parameter space that is underpopulated. There are fewer objects with orbits like Ophio's than the standard models predict. This underpopulation is not a smoking gun. It is a statistical suggestion the outer solar system is incompletely surveyed. Yet the number of objects with orbits like Ophio's is unknown. Ophio may be the first of many, and a larger sample might bring the statistics back into line with predictions. The Vera Rubin Observatory's upcoming surveys will help answer this question definitively, but the underpopulation is suggestive. And the direction in which Ophio's orbital axis points, the specific orientation of its orbit in three-dimensional space, is a detail that the team examined carefully because it is exactly the kind of detail that could distinguish between the influence of known bodies and the influence of something unknown. The orbital axis points in a direction that is, within the uncertainties, consistent with influence from a massive body in a specific region of the outer solar system. And the region is not where Planet 9's most likely position is placed by the current Best-Bedigan and Brown models, but it is not inconsistent with an alternative orbital solution for a Planet 9 class object, one that the uncertainties in the current data cannot rule out. In other words, Ophio's orbit does not confirm Planet 9. It does not refute it. It points, vaguely and imprecisely, at a direction that might matter, in a way that requires more data to evaluate. This is science delivering its least satisfying but most honest result, a suggestion worth investigating, a possibility worth taking seriously, a direction worth pointing a telescope. At this point in the investigation, the intellectual landscape is crowded with competing hypotheses, which is exactly the state science should be in when the data is insufficient for resolution. Let us map that landscape precisely, because the distinctions between the proposals matter. The original Planet 9 hypothesis of Bedigan and Brown proposes a body 5 to 10 Earth masses at approximately 400 to 800 astronomical units, with an orbital inclination of roughly 15 to 25 degrees relative to the solar system's plane, and positioned in a specific region of the sky that current surveys have not yet covered to sufficient depth. This body, if it exists, would be responsible for the clustering and alignment of extreme trans-Neptunian object orbits through a mechanism called secular resonance, the long-period gravitational influence that operates even between objects that never come close to each other. A more recent proposal, which has informally accumulated the name Planet Y in discussion, is different in character. Where Planet 9 is a sub-Neptune class body at great distance, Planet Y is proposed to be smaller, perhaps Earth-sized or even smaller, at a closer distance of roughly 100 to 200 astronomical units. Its proposed effect on the outer solar system is not orbital clustering, but orbital tilting. The orbital inclinations of certain Kuiper belt objects, the angles at which their orbits are tipped relative to the average plane of the solar system, show patterns that are difficult to explain with the known planets alone. Planet Y, in this proposal, would be the body responsible for that tilting through its gravitational influence at intermediate distances. The two hypotheses are not mutually exclusive. Planet 9 could organize the most distant object orbits at the largest scales, while Planet Y tilts the closer Kuiper belt population at smaller scales. They could coexist without contradiction, and there is no physical reason why the outer solar system should contain exactly one undiscovered body rather than 2 or 3 or none. Then there are the non-planet explanations. The galactic tide is real, and its effects on outer solar system objects are measurable. The specific form of the galactic tide in the solar neighborhood, the difference in gravitational pull between the direction toward the galactic center and the direction perpendicular to the galactic plane, imparts angular momentum to the orbits of distant objects in ways that can produce statistical alignments superficially similar to what Planet 9 is supposed to create. But the question is whether the galactic tide alone can produce the specific clustering observed, or whether it requires assistance from an unseen planet. Current models suggest the galactic tide is insufficient on its own, but the models carry uncertainties large enough that a definitive answer requires more data. Passing stars are another mechanism. During the first billion years of the solar system's history, the Sun was part of a stellar cluster, a dense group of stars that formed from the same molecular cloud. Gravitational interactions within that cluster could have scattered outer solar system objects into unusual orbits, imprinting patterns that still persist today. But this mechanism operated billions of years ago, and the patterns it would produce, while qualitatively similar to what is observed, they have specific statistical properties that can be tested against the data. The current consensus is that stellar encounters cannot by themselves explain the entire ETNO clustering. There is also the possibility of leftover primordial chaos. The early solar system was not neatly organized. Giant planet formation and migration was a violent, stochastic process, and the distribution of surviving objects in the outer solar system reflects that violence in ways that may not be fully captured by any current model. The apparent statistical clustering of ETNOs might be a sampling artifact, a selection effect, or simply a residue of primordial chaos that looks like an organizational signal without being one. And then there is the most uncomfortable alternative, the one that planetary scientists discuss carefully and with appropriate caution. Perhaps the standard model of gravity, general relativity supplemented by Newton's laws for the weak field regime of the outer solar system, is not exactly right at these scales. Modified Newtonian dynamics, MOND, and its more sophisticated descendants propose small modifications to how gravity behaves at very low accelerations, exactly the regime relevant to objects at hundreds of astronomical units from the Sun. The modifications are controversial and face significant observational constraints, but they have not been definitively ruled out in the outer solar system context, and a handful of theorists continue to investigate whether MOND-like effects could explain the ETNO clustering without requiring any new massive body. This is not where the mainstream sits, as the mainstream is agnostic between Planet 9 and the non-planet explanations, waiting for better data, while finding the Planet Y proposal interesting enough to take seriously. What OFI contributes to this landscape is a new data point that constrains some proposals and remains neutral on others, and a chemical record that raises a question none of the existing proposals was designed to answer. Where did this object come from exactly? And what does its journey tell us about the journey of the solar system itself? To appreciate what OFI's chemical record implies about the early solar system, it is necessary to understand Neptune's role in the outer solar system's history in detail, because Neptune is the great sculptor of this region of space. Neptune is the most distant of the four giant planets at its current position of approximately 30 astronomical units. It is also the most important gravitational influence on the Kuiper Belt, the scattered disk, and the inner reaches of the Oort cloud. Its gravitational reach, while not as powerful as Jupiter's, extends far enough to affect objects at distances of hundreds of astronomical units through the slow, steady accumulation of gravitational nudges over millions of years. The current Kuiper Belt is shaped like a broad, relatively flat ring extending from roughly 30 to 50 astronomical units, with a classical population of objects in stable, near-circular orbits, and a scattered disk population of objects with more eccentric and inclined orbits. Yet the classical Kuiper Belt objects sit in two groups based on their relationship to Neptune. The cold classical Kuiper Belt objects have very low orbital inclinations, almost perfectly flat orbits, and they are thought to have formed approximately in place, without significant scattering. The hot classical Kuiper Belt objects have higher inclinations, and are believed to have been dynamically excited, scattered into their current orbits by Neptune's migration. The scattered disk, which includes objects like Eris and possibly Ophi at certain periods of its orbit, consists of objects that were scattered inward and outward by close encounters with Neptune during its migration. These objects have orbits that still interact actively with Neptune, being repeatedly pushed and pulled in ways that slowly diffuse their orbits outward over time. At the extreme end of the scattered disk merges into the population of detached objects, bodies like Sedna, whose orbits no longer interact with Neptune in any direct way, and which therefore must have acquired their current orbits through some other mechanism, either gravitational scattering by a Planet 9 class body, or stellar perturbations during the Sun's early cluster environment, or some combination. What Ophi appears to be is an object with a chemically recorded history that spans several of these dynamical regimes. Its surface chemistry, as read by Webb, suggests formation or prolonged residence at distances where Neptune's gravitational influence would have been strong during its migration phase, roughly 20 to 30 astronomical units. Its current orbit places it in the scattered disk or borderline detached population. The impact event visible in its spectrum exposed chemistry from this early formation environment, chemistry that would otherwise be buried under a billion years of cosmic ray processing. The timeline of this chemical signature is the key detail. The cosmic ray clock tells us the surface was exposed within the last 1,000 years. The chemistry preserved under that surface is far older, potentially as old as the solar system itself. The impact that exposed it was recent. The material it revealed was ancient. Webb read a message written 1,000 years ago by a collision that happened to crack open a 4.5 billion-year-old record. This is the actual nature of the 1,000-year-old message. It is not a transmission. It is not a signal in the radio or electromagnetic sense. It is a chemical signature on a frozen surface. It's the product of an impact event 1,000 years ago, preserving chemical information from the era of solar system formation. And the reason it is described as a message is that it speaks, in the language of chemistry, about a history that no other data source could tell. Science at its best is detective work, and the outer solar system in 2025 is a crime scene with very few witnesses. The crime, if we use the metaphor, is the missing history. The solar system we observe today is the result of 4.5 billion years of processes, most of which left no surviving record. The inner planets were melted and remelted by impacts and volcanism. The atmospheres changed. The oceans of the Earth and the ice sheets of Mars came and went. The asteroid belt was depleted by Jupiter's gravitational influence. Neptune migrated. The NICE model describes all of this in broad strokes, but the fine details of what happened and when are poorly constrained. The outer solar system objects, the Kuiper belt bodies, and the scattered disk and the detached populations are the best surviving witnesses. They are cold enough that their formation chemistry is partially preserved. They are distant enough that they have been relatively undisturbed by the inner solar system's chaotic history. They are numerous enough that statistical patterns in their properties can reveal information about the processes that created them. But they are also so cold, so faint, and so distant that reading their chemistry in detail was impossible before Webb. The detective work involves combining multiple lines of evidence. Orbital dynamics tells you where an object has been and what gravitational influences it has experienced. Composition tells you where and in what conditions it formed. Size and shape tell you about the accretion processes that built it. The combination of these three data streams, constrained by physical models and statistical analysis of the full population, is how planetary scientists reconstruct solar system history. Ophi contributes to all three lines. Its orbit constrains the dynamical history. Its size makes it a significant member of the population. And its composition, as read by Webb, provides direct chemical evidence about its formation environment. No single object can tell the whole story, but each object adds information. Ophi adds more information than most because its recent impact event exposed chemistry that would otherwise be buried. The team that analyzed the Webb data approached it in the manner of forensic scientists. They began with the expected spectral features, the baseline composition for an outer solar system object of Ophi's size and estimated age, and subtracted that baseline from the observed spectrum. What remained after subtraction was the anomaly, the signal above and beyond what standard models predict. They then compared this anomaly to a library of reference spectra for compounds known to form under various temperature and radiation conditions, and identified the closest matches. The closest matches were to compounds in a specific class of organic molecules, to carbon-bearing compounds with specific hydrogen and oxygen bonding patterns that form most efficiently at temperatures between 30 and 60 Kelvin under specific radiation flux conditions. Modeling those conditions back into the solar system context, applying the known temperature and radiation gradients at various distances from the Sun during different epochs of solar system history, produced a formation location estimate, 25 to 30 astronomical units, at some point in the solar system's history, before or during Neptune's outward migration. This is the chemical smoking gun. It does not prove that Ophi formed there. It demonstrates that the anomalous compounds on its surface formed under conditions consistent with that region and that epoch. The simplest explanation is that the object carries those compounds because it spent time there. Alternative explanations exist. They always do in science, but they require additional assumptions that the simplest explanation does not. Frank Drake, speaking about the search for extraterrestrial intelligence, once remarked that the most profound discoveries come from taking simple observations seriously. The Webb observation of Ophi is a simple observation taken seriously. It says, "This surface has chemistry it should not have at this distance. That chemistry came from somewhere else. Find that somewhere, and you find a chapter of solar system history that was previously unreadable." History has something useful to say here, and it should be heard before the investigation goes further. In the mid-19th century, astronomers observed that the orbit of Mercury precessed at a rate slightly faster than Newtonian mechanics predicted. The precession was small, 43 arcseconds per century, but it was measurable and it was real. Urbain Le Verrier, the same French mathematician who had predicted the existence of Neptune from the orbital anomalies of Uranus and been triumphantly vindicated in 1846, turned his attention to the Mercury anomaly and reached what seemed like a natural conclusion. If unexplained orbital anomalies had indicated a new planet in the outer solar system, surely unexplained orbital anomalies in the inner solar system indicated a new planet there as well. He proposed a planet between Mercury and the Sun, close enough to the Sun that it would be nearly impossible to observe directly. He called it Vulcan, and for decades astronomers searched for it, occasionally claiming tentative detections during solar eclipses and transits, and never finding anything definitive. Vulcan was needed to explain the data. The data was real. The explanation was wrong. The actual explanation for Mercury's orbital precession came in 1915, when Albert Einstein published the general theory of relativity. Gravity in strong fields, like the field close to the Sun, does not behave exactly as Newton described. The small but measurable deviation from Newtonian predictions produces exactly the precession of Mercury's orbit that Le Verrier had measured. No new planet was needed. A new theory of gravity was needed instead. The Vulcan lesson is this: anomalous observations do not inevitably imply undiscovered objects. They imply that something is missing from the model. Sometimes the missing thing is a new planet. Sometimes it is a new understanding of fundamental physics. Sometimes it is an observational bias. Sometimes it is a combination of factors that no single simple explanation captures. The history of astronomy is full of cases where the first proposed explanation for an anomaly turned out to be wrong, and the correct explanation was something nobody anticipated. This lesson applies directly to Planet 9 and to the interpretation of Ophi's orbital and surface properties. The orbital clustering of ET and O's is a real signal in the data. Ophi's surface chemistry is a real signal in the Webb spectrum. The most obvious explanations for both signals involve something large and distant in the outer solar system. But the Vulcan precedent demands that simpler, less exotic explanations be fully explored before the extraordinary claim of a new planet is accepted. It also demands something else: that if the true explanation is a new planet, that planet must eventually be directly detected. Le Verrier's proposed Vulcan, despite decades of searching, was never found. If Planet 9 exists and has a mass 5 to 10 times Earth's, it should be detectable by sufficiently sensitive surveys. The Vera Rubin Observatory's legacy, survey of space and time, will map the entire accessible sky to unprecedented depth every few days for 10 years. If Planet 9 is out there at the distances and inclinations predicted by Badigan and Brown, Vera Rubin should either find it or produce a null result so stringent that the hypothesis becomes untenable. That survey is underway. The data will come. Until it does, the honest position is the one the investigation has been building toward. The outer solar system contains more than we have seen. And the signals from that hidden population are reaching us in new ways through new instruments, and the interpretation of those signals requires both imagination and rigorous skepticism in equal measure. How do you find something you cannot see? This is the operational question that defines outer solar system research, and the answers to it have changed substantially in the last 2 decades. The classical method is direct imaging. You point a telescope at a patch of sky, take repeated images over hours or days, and look for an object that moves against the fixed background of stars. Everything in the solar system moves relative to the stars, because everything in the solar system is orbiting the sun, and objects at different distances from the sun move at different rates. Yet the apparent motion of a solar system object on the sky is a direct function of its distance. Nearby objects move fast, distant objects move slowly. An object at 100 astronomical units moves so slowly that detecting its motion requires observation separated by weeks or months. The technique works, but it has a fundamental sensitivity limit. Solar system objects at great distances are faint, and they are faint for 2 reasons. First, they receive less sunlight because sunlight intensity falls off with the square of the distance. An object at 100 astronomical units receives sunlight 10,000 times fainter than an object at 1 astronomical unit. Second, the reflected sunlight travels back to Earth over another 100 astronomical units, falling off again with the square of the distance. Yet the total received brightness falls off as the 4th power of the distance. An object 10 times further away appears 10,000 times fainter in reflected light, all else being equal. This means that a Pluto-sized object at 500 astronomical units is roughly 25 times fainter than Pluto itself, already challenging for most ground-based telescopes. Infrared observations partially circumvent this problem. At infrared wavelengths, you are not detecting reflected sunlight, but thermal emission, the heat radiated by the object's surface. Surface temperatures in the outer solar system fall much more slowly with distance than reflected brightness does, because temperatures depend on the square root of solar flux rather than linearly. And an object at 100 astronomical units has a surface temperature roughly 3 times lower than an object at 10 astronomical units, while its reflected brightness is 10,000 times lower. For cold outer solar system bodies, infrared telescopes see them more easily than optical ones. This is where Webb's capabilities become decisive. Webb's primary scientific instruments include spectrographs operating at wavelengths from 0.6 to 28 microns, covering the near-infrared and mid-infrared range with sensitivity orders of magnitude beyond previous space telescopes. At these wavelengths, the thermal emission from outer solar system bodies becomes accessible, and the spectroscopic resolution Webb achieves is sufficient to identify specific molecular species on their surfaces. No previous instrument combined Webb's mirror size, its spectroscopic resolution, and its infrared wavelength coverage in a way that made the chemical characterization of distant small bodies possible. The IRS satellite, launched in 1982, conducted the first all-sky infrared survey and identified candidate objects in the outer solar system that were never fully followed up. The Akari satellite, a Japanese instrument from the 2000s, repeated this exercise with better sensitivity. Both missions found hints of objects at extreme distances, some of which were subsequently confirmed as comets or Kuiper belt objects, and some of which remain on lists of candidates awaiting confirmation. The Architects program designed to use Webb includes a component that revisits some of these historical candidates, and applying Webb's spectroscopic capabilities to objects first noticed 40 years ago and never properly characterized. One of those historical candidates is particularly relevant to the Planet 9 question. An IRAS object from 1983, not assigned to any known comet or asteroid, sitting in the database as an unresolved point source at far infrared wavelengths, was flagged in a 2022 analysis as potentially consistent with a large cold body at several hundred astronomical units from the Sun. The positional uncertainty is large and the data quality is poor by modern standards, but the object, if real, would have an apparent brightness at infrared wavelengths consistent with a Neptune-class body at extreme distance. The Architects program includes a Webb observation targeting the most probable position range for this historical candidate. That observation had not yet been conducted as of the time this investigation was being written. Its results will be among the most consequential in the Planet 9 debate. If Webb finds a large cold body at that location, the entire conversation changes. If Webb finds nothing, the historical IRAS candidate joins a long list of outer solar system ghosts, signals that turned out to be noise, candidates that did not survive the scrutiny of better instruments. The parallax correction technique, mentioned briefly in the discovery context of Ophi, deserves specific explanation. When observations of an object are separated in time, the Earth has moved around the Sun, changing the viewing angle. This change in angle produces an apparent shift in the position of the object against background stars, the shift being larger for closer objects and smaller for more distant ones. By measuring the magnitude of this shift, called parallax, and using geometry, you can calculate the distance to the object without any other information. Ophi's parallax was measured from the archival data that confirmed its existence, and the measurement was what established its distance with enough precision to calculate the orbital solution. But parallax measurement at extreme distances is technically challenging. An object at 90 astronomical units shows a parallax of about 40 arcseconds annually, which is large enough to measure easily with modern instruments. An object at 500 astronomical units shows a parallax of about 8 arcseconds, still measurable but requiring careful calibration. An object at 1,000 astronomical units shows a parallax of about 4 arcseconds, at the edge of what ground-based telescopes can measure reliably, and requiring observations separated by at least 6 months to cover the full baseline of Earth's orbit. This is one reason why a Planet 9 class object at 400 to 800 astronomical units is so difficult to detect definitively. Its parallax is small. Its reflected brightness is extremely faint. Its thermal emission is at wavelengths that require specialized infrared telescopes, and its orbital motion is so slow that distinguishing it from a background galaxy requires observations separated by years. The window for detecting it is narrow. The required sensitivity is at the edge of current capabilities, and the sky is large. Science is not a monologue. The Planet 9 debate, and the interpretation of Ophi, and the implications of the Webb data, all of these are contested in the genuine scientific sense, meaning that researchers with different analyses of the same data reach different conclusions, argue publicly and in journals, revise their models in response to each other's criticisms, and update their positions as new information arrives. This is not weakness. This is the mechanism by which science approaches truth. The case for Planet 9 remains strongest in the work of Badigan and Brown themselves, who have continued to update their models as new ETNOs are discovered and as the statistical analysis of orbital clustering becomes more refined. Their most recent models place Planet 9 at a somewhat different location in mass than the original 2016 paper. The position estimate having shifted as the sample of constraining ETNOs has grown, the mass estimate having narrowed as better dynamical models are applied. They continue to argue that the clustering signal is real, that it cannot be explained by observational bias alone, and that a Planet 9 class body is the most parsimonious explanation. Against this, Anne-Marie Madigan and colleagues at the University of Colorado have proposed that the clustering of ETNOs can be explained by a mechanism called collective gravity, the combined gravitational influence of the entire ETNO population on itself, without any single massive body. In this model, the ETNOs are self-organizing, their mutual gravitational interactions slowly herding them into correlated orbit orientations over long time scales. The mechanism is real physics, and in toy models it produces clustering qualitatively similar to what is observed. The debate about whether it can produce clustering of the observed magnitude and character remains unresolved. Samantha Lawler and colleagues at the University of Regina have argued most persistently that the Planet 9 signal in the ETNO data is a selection effect, that the specific observational biases of the surveys that discovered the clustered ETNOs are sufficient to produce the apparent clustering without any real dynamical signal underlying it. Their simulations of survey biases are careful, and the point they are making is technically important. The surveys that found the clustered ETNOs were not random surveys of the sky. They targeted specific regions more than others. They had specific magnitude limits that favor certain kinds of objects, and they covered certain ranges of orbital parameter space more thoroughly than others. If those biases are not fully accounted for, a statistical signal that looks real might be an artifact of the survey design. This is the most fundamental disagreement in the field, and the one that more data most directly addresses. When Vera Rubin completes several years of its all-sky survey and provides a sample of ETNOs several times larger than the current one, discovered in a survey with well-characterized biases and much broader sky coverage, the selection effect argument either survives with new data to support it or collapses under the weight of a statistically robust clustering signal. Into this ongoing debate, OFI arrives as a new data point, whose implications depend on which side of the debate you are standing on. For the Planet 9 proponents, OFI's anomalous orbit orientation is at worst neutral and at best another data point constraining the planet's position. Its surface chemistry is an interesting compositional measurement that speaks to solar system formation history and to Neptune's migration, which is background context rather than specific evidence for or against Planet 9. For the skeptics, OFI's orbit being inconsistent with the specific Planet 9 predictions of the Battigan-Brown model is mild evidence against the hypothesis, or at least against the specific orbital solution those models favor. Not falsifying, but not confirming, and the inconsistency adds to the accumulating picture of an outer solar system that is less neatly organized than the Planet 9 hypothesis requires. For the dynamicists studying solar system formation, regardless of their position on Planet 9, OFI's Webb-characterized surface chemistry is the most interesting datum. It is a direct measurement of formation conditions that previous analyses could only infer from orbital dynamics, and it provides a calibration point for models of Neptune's migration and the early Kuiper Belt environment that no previous object has provided as clearly. This is why the investigation refuses to resolve cleanly. The data is not clean. The outer solar system is not clean. It is a chaotic, partially preserved, incompletely surveyed relic of a violent history, and our best instruments are only beginning to read its record in the detail it deserves. At this point, it is necessary to take a brief but deliberate detour into a landscape that exists in the popular imagination but not in any scientific database, because the subjects of outer solar system objects and hidden planets reliably attract a category of speculation that deserves honest engagement rather than dismissal. Nibiru is not real. This statement requires no qualification or hedge. The notion that a planet is on an imminent collision course with Earth, crossing the inner solar system every few thousand years, and causing catastrophes on geological and historical timescales, has no basis in observational data, violates basic orbital mechanics, and has been proposed and refuted so many times that the academic literature no longer bothers to respond to it. An object on a close approach orbit with Earth would have been detected by dozens of surveys. It would be visible to amateur astronomers with modest equipment. It would be affecting the orbits of Earth's moon, Venus, Mars, and every other body in the inner solar system in ways that are precisely measurable and completely inconsistent with the actual observed orbits. The physics makes Nibiru impossible. The observations make Nibiru impossible. It is not Planet 9. It is not OFI. It is not any other legitimate outer solar system candidate. The Phaeton, or Phaeton hypothesis, the idea that an ancient planet between Mars and Jupiter was destroyed and its remains form the asteroid belt, is more historically interesting but equally wrong scientifically. The asteroid belt contains too little mass to have ever constituted a planet, and the compositional diversity of asteroids suggests they formed at different distances from the Sun and were never part of a single coherent body. Dynamical models show that Jupiter's gravitational influence prevented a planet from ever forming at those distances, rather than destroying one that had already formed. This hypothesis has been dead in the scientific literature for decades. Nemesis, the hypothetical companion star to the Sun proposed in the 1980s to explain apparent periodicity in mass extinctions on Earth, is a different kind of story. Unlike Nibiru, it was proposed by serious scientists for serious reasons, and investigated seriously before being rejected by data. The proposed mechanism was an M-dwarf, or brown dwarf, companion orbiting the Sun at about 1.5 light-years, and periodically perturbing the Oort cloud and sending showers of comets into the inner solar system on a roughly 26 million-year period, causing mass extinctions as the comets bombarded Earth. The hypothesis was tested by infrared sky surveys looking for the thermal signature of such a companion and found nothing. Nemesis is considered dead by the scientific community. Though the periodic extinction hypothesis it was designed to explain remains debated. Rogue planets are real. This is different. Free-floating planets, objects of planetary mass not gravitationally bound to any star, have been detected by microlensing surveys and direct imaging in star-forming regions. The Milky Way may contain as many free-floating planets as it contains stars, according to some estimates. Some of these objects could be captured by stars during close gravitational encounters, becoming bound members of a solar system without having formed from that system's disk. Whether our solar system has captured any such objects is unknown. The outer Oort cloud, if it exists as modeled, would be a plausible reservoir for captured objects, though demonstrating that any specific object was captured rather than formed in place is currently impossible. This matters for the Planet 9 discussion because one alternative explanation for a Planet 9 class body, if it exists, is that it is a captured rogue planet rather than a planet that formed from the solar system's own disk. The chemical composition of such an object would be different from a solar system native, reflecting the composition of the disk from which it originally formed around a different star. Webb pointed at a confirmed Planet 9 candidate might be able to distinguish these scenarios. The surface chemistry of a captured rogue planet would carry the isotopic and molecular fingerprints of a different stellar environment, in principle distinguishable from the solar system baseline. This is speculative, but it is scientifically speculative, meaning it makes testable predictions. If Planet 9 exists, and Webb can characterize its surface, the chemical record could tell us whether it formed around our sun or around someone else's. That is not science fiction. That is the current frontier. Before we return to the specific implications of Ophi and the Webb data, there is a practical question worth addressing. And because the outer solar system is not only scientifically fascinating, it is, in the long view, economically and strategically significant in ways that are beginning to register in the planning documents of space agencies and private companies. Ceres sits at the inner edge of the asteroid belt, roughly 2.8 astronomical units from the Sun, closer to us by far than any of the Kuiper Belt objects. It is the largest body in the asteroid belt, with a diameter of about 940 kilometers, and it was classified as a dwarf planet in the same 2006 IAU ruling that reclassified Pluto. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018 and revealed a world of extraordinary complexity. Bright spots and craters now understood to be reflective salts deposited by briny water that periodically seeps to the surface, and a surface rich in ammoniated phyllosilicates, suggesting that Ceres or its material may have formed in the outer solar system and migrated inward, a thin transient atmosphere of water vapor detected during perihelion. The water is the thing that matters for the long-term human story. Ceres is estimated to contain more fresh water, in the form of ice, than exists in all of Earth's freshwater reserves combined. At a gravity of roughly 3% of Earth's, getting material off Ceres is energetically cheap. It is close enough that travel times from Earth are measured in months rather than years. It sits in the asteroid belt, surrounded by metallic asteroids that contain iron, nickel, cobalt, and platinum group metals in concentrations that dwarf anything accessible on Earth's surface. The vision for Ceres as a logistics hub for deep space operations is not fanciful. It is the subject of serious engineering studies. A base on Ceres could refine water into hydrogen and oxygen for rocket propellant, providing a refueling depot for missions deeper into the solar system. It could process the surrounding asteroid material to extract construction materials and metals for in-situ manufacture. It could serve as a staging point for crewed missions to Jupiter's moons, to the Kuiper Belt, to the eventual targets of human exploration in the outer solar system. The challenges are real and significant. The radiation environment at Ceres is more intense than on Earth's surface. The low gravity, while useful for launch, creates physiological problems for long-term human habitation. And the distance from Earth means communication delays, measured in minutes to tens of minutes, and resupply timelines measured in months. The cost of establishing any permanent infrastructure in the asteroid belt with current launch technology is enormous. But these are engineering challenges, not physical impossibilities. They are the kind of challenges that respond to investment in time in ways that the physical impossibilities, like faster-than-light travel, do not. The history of human exploration is a history of overcoming exactly these kinds of challenges, and the outer solar system represents the next chapter of that history in a way that the same century that saw the first powered flight and the first moon landing makes at least plausible within some foreseeable future. And more immediately relevant to this investigation is what robotic exploration of the Kuiper Belt would look like. The New Horizons spacecraft, which flew past Pluto in 2015, and the Kuiper Belt object Arrokoth in 2019, demonstrated that robotic missions to the outer solar system are feasible and scientifically enormously productive. Arrokoth, the most distant object ever examined by a spacecraft, turned out to be a contact binary. Two lobes gently merged at low velocity, its red surface chemistry consistent with the radiation processing models that predict Tholen-covered outer solar system objects. The information returned by New Horizons about these objects in two brief flybys revolutionized the understanding of primordial solar system bodies, a mission to Ophi if one were ever funded and launched. It would take on the order of 20 to 30 years to arrive at its current position using conventional propulsion. The orbital solution required to intercept an object with Ophi's extremely elongated orbit is complex, and the transfer trajectory would need careful design. But such a mission is not beyond current capabilities in principle. The scientific return would be extraordinary. A close approach to Ophi would allow direct sampling of the surface chemistry that Webb has characterized from Earth orbit, ground-truthing the spectroscopic interpretations, and providing isotopic measurements that spectroscopy alone cannot make. And a direct sample of the formation chemistry of the inner Oort cloud edge, the region where Neptune scattered objects to during its migration, that would be a scientific return comparable to what the Apollo lunar samples provided for understanding the formation of the Moon. It would be a message from the beginning of the solar system, delivered directly into the hands of scientists, rather than read from 90 astronomical units away through an infrared spectrograph. We are standing at an unusual moment in the history of solar system science. The instruments finally exist to read chemical records that have been sitting in the outer solar system for billions of years. The data pipeline from Webb to spectral analysis to dynamical interpretation is beginning to produce results. The first full survey of the outer solar system to sufficient depth is now underway with the Vera Rubin Observatory's LSST. The theoretical models of solar system formation, while still contested on details, and have converged on a broad picture that the observations are beginning to test systematically. The broad picture is this. The solar system formed from a disk of gas and dust roughly 4.6 billion years ago. The inner planets formed from rocky, refractory material. The giant planets formed in the outer disk, where ices were available, and grew large enough to accrete gas before the sun cleared the disk. The giant planets then migrated, scattering the primordial Kuiper Belt, populating the Oort cloud, and producing the late heavy bombardment of the inner planets. The current configuration is the stable end state of this dynamical evolution, at least for the next several billion years, when the sun's increasing luminosity will begin to affect the inner planets. And this picture makes specific predictions about the chemical composition of objects in different regions of the solar system. Objects in the classical Kuiper Belt should have compositions reflecting formation at 40 to 50 astronomical units in the cold outer disk beyond Neptune. Objects scattered outward from closer formation sites should carry the chemical record of those closer environments. Objects in the inner Oort cloud might carry records of the specific scattering events that put them there, potentially including information about the early stellar cluster environment the Sun inhabited. Ophi, as a scattered disk or inner Oort cloud object with a chemical record suggesting formation at 25 to 30 astronomical units, fits into this picture in a specific way. It is, potentially, a messenger from the epoch of Neptune's migration, carrying on its surface, preserved by cold and ice and the accident of a recent impact, the chemistry of a solar system configuration that ended billions of years ago. The broader Architects program, of which the Ophi observations are one component, is designed to build a systematic chemical library of these objects. When enough objects have been characterized by Webb, patterns will emerge. The distribution of chemical signatures across the outer solar system will map with some statistical confidence, to different formation locations and different epochs. The picture of solar system history that emerges from this mapping will be tested against the dynamical models and will either confirm them, refine them, or force revisions that no theorist has yet anticipated. This is how science works at its best. An instrument of extraordinary sensitivity pointed at objects previously too faint to characterize, a systematic program of observation, building a library of data, theoretical models making testable predictions, the observations testing those predictions, the comparison producing either confirmation or the need for revision. The outer solar system is the site of this investigation right now, in 2025 and 2026, and the investigation is early enough that its most important results are still ahead. The Vera Rubin Observatory will find hundreds of new Kuiper Belt objects every year, among them many new ETNOs. Webb will characterize the most scientifically interesting of those objects in spectroscopic detail. The Architect's Catalog, when complete, will be one of the most important data sets in the history of planetary science. And somewhere in that data set, or perhaps in the directly detected signature from one of the current surveys, the answer to the Planet 9 question may finally become clear. In the fall of 2024, before the discovery of Ophi and before the Webb observations of the Architects program had produced their full results, a team analyzing data from infrared sky surveys reported something that had been sitting unrecognized in the archival data for years. The object was not bright. It was a faint, unresolved source at far infrared wavelengths, sitting in data from the IRAS satellite survey conducted in 1983 and the Akari survey from the early 2000s. Its position in the sky was not particularly interesting, a region without remarkable foreground stars or known solar system bodies. But when the team applied a parallax correction, and accounting for the change in Earth's position between the 1983 IRAS observation and the 2006 Akari observation, the source shifted. It moved, not by much, but by enough. Moving background infrared sources are not common. Moving infrared sources that move at the precise angular rate consistent with an object at several hundred astronomical units from the Sun are rarer still. The team calculated an approximate distance. The parallax shift was consistent with an object at roughly 700 astronomical units. The brightness, converted to a temperature using standard models for cold bodies at that distance, was consistent with a Neptune-class object, something in the size range of 50,000 to 80,000 kilometers in diameter, roughly Neptune-sized. They were careful. They published a paper that described the candidate, laid out the data, explained the parallax method, listed the uncertainties, and explicitly declined to call it a discovery. It was a candidate. The data was from archival surveys, with limited positional accuracy. The detection was marginal by the standards of modern instrumentation. Confirmation would require pointing a current telescope at the candidate's expected position, accounting for its projected motion since 2006, and either detecting it or not. The paper made this candidate the most discussed object in the Planet 9 community since the Badigan-Brown proposal in 2016. If confirmed, it would be one of the most important discoveries in the history of astronomy, a planet larger than Neptune hiding in the outer solar system for the entire modern era of planetary science. The Architects program had Webb observation time allocated. The team, but in consultation with the broader outer solar system community, added the candidate position range to their target list. The observations required to confirm or rule out the candidate were feasible within Webb's capabilities. The expected position of the object in 2024 and 2025, extrapolated from the 2006 position using the estimated orbital velocity at 700 astronomical units, was within the region of sky Webb had already been observing for the Architects program. The results of those observations, as of the time this investigation was written, had not been made public. They were known to the team and were in preparation for submission to a journal. The scientific community was waiting. This is the frontier, not the confirmed discovery, not the resolved question, but the frontier. The observation has been made. The data exists. Yes, the analysis is being done. The answer to one of the most important questions in modern planetary science may be sitting in a hard drive at someone's institution, waiting for the paper to be finished, the peer review to be completed, the announcement to be prepared. Science advances like this. not in the dramatic moment of looking at a screen and seeing an unknown world. In the grinding work of data reduction, systematic error checking, comparison against alternative explanations, careful writing of methods sections and uncertainty estimates, the slow building of certainty from ambiguous data. The moment of discovery, when it happens, is real, and it is significant. But it is preceded by months of work that nobody sees, and followed by months more before the rest of the world knows. The outer solar system is waiting. The instruments are ready, the candidates are identified, the resolution is imminent, if not in this month, then in the next few years, if not from this specific candidate, then from the hundreds that Vera Rubin will produce. The Kuiper Belt is not empty. This is the most important single sentence in the study of the outer solar system, and it is a sentence that every generation of astronomers has had to discover anew, each time with more data and more surprise. When Gerard Kuiper proposed in 1951 that there might be a belt of icy bodies beyond Neptune's orbit, the idea was theoretical. The belt was assumed to be the source of short-period comets, objects that had been nudged inward by Neptune's gravity and were slowly making their way toward the Sun on shorter and shorter orbits. But the belt itself, the objects composing it, they were hypothetical. No Kuiper Belt object had ever been observed. The first confirmed Kuiper Belt object beyond Pluto was found in 1992. By the late 1990s, dozens had been found. By 2005, hundreds. By 2015, thousands. The census has continued to grow, driven by improving survey technology and increasingly deep sky coverage, and the picture of the Kuiper Belt that has emerged from this census is richer, more complex, and more dynamically structured than anyone imagined in 1951. The classical Kuiper Belt objects, the cold population in nearly circular orbits, show a striking property. They are almost exclusively binary or contact binary systems. A significant fraction of classical Kuiper Belt objects consist of two components orbiting each other at close range. This is thought to be a remnant of the streaming instability formation mechanism, the process by which turbulent flows in the protoplanetary disk concentrated material into clumps that directly collapsed into planetesimals rather than accumulating grain by grain. Binary systems form naturally in this process, and their survival in the cold classical Kuiper Belt, where collision velocities are low and disruption is rare, records the formation mechanism directly. The hot classical Kuiper Belt objects, scattered into their higher inclination orbits by Neptune's migration, show a different property. They are more compositionally varied, with a broader range of surface colors and spectral types. This diversity reflects the diversity of formation locations from which they were scattered. Out sampling different parts of the early protoplanetary disk, the scattered disk objects, of which Ophi is a probable member, have the most extreme properties. Their orbits take them from close encounters with Neptune at perihelion to the inner Oort cloud at aphelion, and the gravitational influence of Neptune continuously works on them, slowly changing their orbits over millions of years. Some scattered disk objects will eventually be directed inward to become active comets. Others will be ejected from the solar system entirely. A small fraction will evolve into the detached population, their perihelia lifted away from Neptune's influence by some mechanism, possibly Planet 9, possibly the galactic tide, possibly stellar perturbations during the Sun's early cluster life, into orbits like Sedna's that are stable for billions of years. And beyond all of this, in the unmapped territory beyond 100 astronomical units, is a population of objects we cannot currently see. The models predict they exist. The dynamics of solar system formation requires that they exist. But their characterization has to wait for either very long observation times with current instruments or the improved sensitivity of next-generation surveys. Webb has made the first substantial contribution to this characterization with objects like Ophi. The Roman Space Telescope, with its wide-field infrared capabilities, will make systematic contributions to the census of this outer population in the coming decade. And in the unmapped territory beyond even that, in the hypothetical zone where Planet 9 might orbit, between 400 and 800 astronomical units, there is either a major planet or there is not, and in either answer has profound implications for everything we think we know about solar system formation, about the early solar system's dynamical history, and about the mechanisms that produce the outer solar system configuration we observe today. Science at the frontier looks nothing like science in the textbook. In the textbook, results are clean, conclusions are definitive. The narrative moves from hypothesis to experiment, to confirmation, to knowledge. At the frontier, results are ambiguous, conclusions are contested. The narrative moves in circles and spirals, revisiting the same questions from new angles as data accumulates. Each new instrument revealing something unexpected that requires the circle to widen before any conclusion can be trusted. This is where the outer solar system science of 2025 and 2026 sits. The Planet 9 hypothesis is 9 years old and unconfirmed. The strongest evidence for it, the orbital clustering of ETNOs, has been alternatively explained by selection bias, collective dynamics, and primordial chaos, none of which explanations is fully satisfying, and none of which is definitively eliminated. The searches for the planet directly have found nothing, which is either absence of evidence or evidence of absence depending on how completely the relevant sky has been covered. Ophi's discovery adds complexity rather than clarity. An orbit that does not fit the Planet 9 prediction as the current models specify it, a surface chemistry that speaks to solar system formation history, but not to any currently proposed hidden planet. The Webb data on Ophi is real. The anomalous compounds are real. The inference about formation conditions is a careful interpretation, not a certainty, but it is grounded in well-understood chemistry and calibrated against laboratory measurements of compound formation rates under specific temperature and radiation conditions. The cosmic ray clock is a real technique with a well-established theoretical basis and empirical calibrations from lunar surface samples and returned comet material. The conclusion that Ophi's surface was disturbed by an impact within the last 1,000 years is a specific, testable prediction that additional observations can evaluate. What is not real, what exists only as possibility, is the specific inference about where Ophi formed. The anomalous chemistry is consistent with formation at 25 to 30 astronomical units during Neptune's migration phase. It is also consistent, to a lesser degree, with a formation site at somewhat different distances and epochs. The chemistry provides a constraint, not a determination. The constraint is useful and informative, but it does not close the question. The Planet 9 question remains open. The probability that it exists has been refined by 9 years of additional data, refined in the direction of lower mass estimates and adjusted position estimates rather than higher probability of existence. The scientific community is more cautious about the hypothesis than it was in 2016, more aware of the selection bias concerns, more attentive to the requirement for a complete sky survey before any statistical conclusion can be trusted. The Vera-Rubin Observatory is the decisive instrument. When it has been operating for 5 years and has produced a sample of ETNOs 10 times larger than the current one, discovered with well-characterized selection functions across the full observable sky, the question will be answerable in a way it is not currently. Either the clustering signal will persist in the larger, less biased sample, demanding explanation by a physical mechanism, or it will fade away as the sample becomes more representative of the full population, dissolving into the background noise of a dynamically complex but planetless outer solar system. That resolution is years away. In the meanwhile, the question is open, the debate continues, and new data from instruments like Webb keeps arriving and demanding integration into a picture that is not yet complete. In the mountains of northern Chile, on a peak called Cerro Pachón, at an altitude of 2,715 meters, a building the size of a small concert hall houses an instrument that will transform planetary science in ways that researchers are only beginning to anticipate. The Vera C. Rubin Observatory, named for the astronomer who discovered the first strong evidence for dark matter from galaxy rotation curves, is built around an 8.4-meter primary mirror and a camera with 3.2 billion pixels, the largest digital camera ever constructed for an astronomical facility. The camera's field of view covers an area of sky roughly 9.6 square degrees, about 40 times the area of the full moon, in a single exposure. The system can image this enormous field in 15-second exposures and then move to the next field in under 5 seconds. The result is a telescope that can cover the entire accessible southern sky every 3 to 4 nights, repeatedly and systematically, building up a database of every detectable object in that sky, tracking how they change over time. This capability is revolutionary for solar system science. Moving objects stand out against the fixed stars because they change position between exposures. The Rubin Observatory's data pipeline is designed to automatically detect and catalog moving objects, building orbital solutions as additional detections accumulate, and distinguishing solar system objects from transient phenomena like supernovae and variable stars. The predicted yield over 10 years of the legacy survey of space and time is staggering. Millions of new asteroids, hundreds of thousands of new Kuiper Belt objects, and potentially dozens of new ETNOs at distances relevant to the Planet 9 debate. The specific relevance to Planet 9 is that the LSST will provide, for the first time, a sample of ETNOs large enough and discovered by a survey uniform enough that the selection bias arguments lose their force. If the orbital clustering of ETNOs is a real dynamical signal, it will be apparent in the Rubin sample. If it is a selection effect of previous surveys, it will not survive in the Rubin data. The answer will come, and it will be based on a sample of perhaps 200 or 300 well-characterized ETNOs discovered in a survey specifically designed to minimize the systematic errors that plague the current smaller samples. Vera Rubin will not find Planet 9 directly, or rather, if it does find a large object at hundreds of astronomical units, that will be serendipitous rather than by design. The survey is optimized for faint, rapidly moving objects in the inner solar system in the relatively nearby Kuiper Belt. A Planet 9 class body at 600 astronomical units moves too slowly against the background stars for the standard LSST detection pipeline to register it efficiently, and it may be at a brightness below the survey's detection threshold, depending on its size and surface reflectivity. Detecting Planet 9 directly may require targeted observations with specific search strategies of the kind that dedicated Planet 9 search programs have been conducting for years. The Nancy Grace Roman Space Telescope, NASA's next major space-based observatory after Webb, will contribute differently. A Roman's primary science goals are cosmological, studying dark energy and dark matter through wide-field surveys of galaxy distributions and gravitational lensing. But its wide-field infrared camera, with a field of view several times larger than Hubble's combined with sensitivity comparable to Webb's at near-infrared wavelengths, will make it enormously useful for outer solar system science. Roman can conduct deep infrared surveys of the outer solar system faster than any previous instrument, and targeted programs for Planet 9 detection have been designed and advocated for its observing queue. Webb itself will continue contributing. The Architects program is designed for multiple years of observations, building the chemical library of outer solar system objects that will eventually provide the compositional context for interpreting any new discovery. When Vera Rubin finds new ETNOs, the most interesting ones will be added to Webb's target list for chemical characterization. The combination of Rubin's discovery pipeline and Webb's chemical characterization capability is exactly the kind of multi-instrument, multi-wavelength approach that planetary science has needed for the outer solar system. Return now to Ophio's surface, to the message that Webb read in the infrared light scattered back from a frozen body 90 astronomical units from Earth, written 1,000 years ago by the impact of something smaller that cracked open the chemistry of a 4.5 billion-year-old interior. The message says several things simultaneously. And it says that this object formed somewhere warmer, at conditions consistent with the inner Kuiper Belt precursor at the time of Neptune's migration. This is information about the early solar system that no previous observation could provide for an object at this distance and in this dynamical state. It says that the outer solar system contains objects whose surface records can be read by Webb on 1,000-year timescales, making the solar system's chemical history accessible in a new way. This is information about methodology, about what Webb can do that no previous instrument could. It says that the object was struck by something within the last millennium, exposing its interior. This is information about the impact environment in the scattered disk, a region where collision rates and impact speeds have been poorly constrained. And it says that the outer solar system is more actively evolving, more recently disturbed, more dynamically alive than it sometimes appears from the perspective of geological timescales. Things are happening out there. Objects are colliding. Surfaces are being refreshed. The cosmic ray clocks are being reset. The outer solar system is not a static deep freeze. It is a slowly churning archive. This last point has implications for the broader Planet 9 question that are easy to overlook in the excitement about the surface chemistry. If collision events are regularly refreshing the surfaces of scattered disk objects on thousand-year timescales, then the surfaces being characterized by Webb represent a shorter temporal window than previously assumed. The chemistry they preserve is more recent, not the chemistry of formation, but the chemistry of the recent interior, exposed by recent disturbance. This changes what spectroscopic surveys can and cannot tell us. It means specifically that using spectroscopy to trace the formation locations of outer solar system objects requires modeling the impact and resurfacing history as well as the chemical formation history. A body whose surface was refreshed 500 years ago carries a different spectral record than one whose surface has been undisturbed for 1 billion years, even if both objects formed in the same place under the same conditions. The architect's program will need to account for this by developing models of surface evolution that include impact resurfacing as well as cosmic ray processing and thermal evolution. This is the kind of complication that advances science. And each new observation reveals new complexities that require new modeling, which makes sharper predictions, which require new observations to test, which reveal new complexities. The cycle has no end in the direction of deeper understanding. Ophi's message is specific and detailed, but what it opens is a conversation about methodology and interpretation that will run for years. The chemical record of the outer solar system, now readable by Webb in more detail than was ever previously possible, is going to be far richer and far more complex than anyone anticipated before the architect's program began returning data. Frank Drake asked his question at a lunch table in 1950, and nobody had a satisfying answer 75 years later. Fermi's paradox persists, not because we haven't looked hard enough, but because the more carefully we look, the more precisely we understand the dimensions of what we don't know. The outer solar system poses a question in the same spirit, not as existentially significant as the silence of the cosmos, but in the same structural form. We know the solar system formed. We know its rough history. We know the major bodies and their orbits, and, increasingly, their compositions. And yet, at the edges of what we know, at the distances where our surveys thin out, and the catalog of discovered objects represents a small fraction of the actual population, there may be things that would change the picture significantly. Planet 9 may or may not exist. The evidence is genuinely ambiguous, which means it is genuinely scientific, which means it is alive, under investigation, worth taking seriously without overclaiming in either direction. At the orbital clustering that motivated the hypothesis is a signal in the data. Whether the signal is dynamical or observational, real or artifact, will be answered in the next decade. That answer will be one of the most significant results in planetary science of the early 21st century, regardless of which direction it falls. Ophi exists. Its orbit is measured. Its surface has been characterized by Webb. The chemical record preserved on that surface speaks to a specific chapter of solar system history, the epoch of Neptune's migration, the scattering of the primordial Kuiper belt, the architecture of a solar system that looked different from the one we inhabit now. That record is imperfect and requires careful interpretation. But it is real data. It is a real message. And it was sitting 90 astronomical units away. It's orbiting the sun in an ellipse that takes 25,000 years to complete, visible to humanity only since 2025, readable by Webb only since November of that year. The question that remains is not simply whether Planet 9 exists. It is what the outer solar system actually is, in full. How many bodies are out there at distances where current surveys cannot see? What chemical records do they carry? What do those records say about the history we can no longer observe directly? How far does the sun's gravitational influence extend? And what is in the space between that influence and the nearest star? Sedna, discovered in 2003, sits at such an extreme distance, with such a large perihelion, that it can only have reached its current orbit through some mechanism beyond the standard gravitational history of the known planets. Whatever put Sedna where it is, whether Planet 9, the Sun's birth cluster, a passing star, or some combination we haven't imagined, also put other objects nearby. Sedna is almost certainly not alone. Its orbit is a signpost to a population, and that population is the next great frontier of solar system science. The Vera Rubin Observatory is mapping. Webb is reading. Roman is coming. The tools are being pointed. The messages are being decoded. And somewhere in the data that will arrive over the next 10 years, the answer to whether our solar system has a ninth planet, to where Ophi came from, to what population Sedna belongs to whether the inner Oort cloud has a coherent structure or is simply the debris field of a billion years of gravitational scattering, those answers are waiting. There's a moment described by researchers who work on outer solar system objects that has no equivalent in other areas of astronomy. It is the moment when you look at the data reduction screen and see a faint point moving against the star field, a point whose motion rate and direction translate, through a parallax calculation, into a distance of 60, 70, 80 astronomical units, beyond Neptune, beyond the classical Kuiper belt. In the territory where surveys are thin and the catalog is incomplete, you are seeing something that most likely no human instrument has ever detected before. The feeling is reported as a kind of quiet vertigo, not the dramatic disorientation of a major unexpected discovery, but something steadier and stranger. The knowledge that you are looking at a world that has been orbiting the sun since before Earth existed, that has been cold and dark and unknown for 4.5 billion years, and that you are the first to have found it. Ophi's discovery team reported something like this: not drama, quiet. That quiet is appropriate, because what the outer solar system represents is not spectacle but depth, the depth of time, the depth of space, the depth of the record preserved in frozen chemistry on surfaces no one has visited, and no one may visit for centuries, if ever. James Webb is not a romantic instrument. It is a machine of extreme precision, cooled to near absolute zero, operating in the L2 Lagrange point, receiving electrical signals from its detectors, transmitting those signals to Earth, where software converts them into spectra, and then researchers compare those spectra to laboratory measurements of compound formation rates at specific temperatures and radiation fluxes. There is nothing romantic about the process. There is nothing mystical about the chemistry. But the result of that process, the reading of a chemical message written 1,000 years ago, by an impact on a frozen world 90 astronomical units from Earth, a message that preserves information about a solar system configuration that ended 4 billion years ago. That result is something that resists purely mechanical description. It is a conversation across time and space, conducted in the language of chemistry, between a world that has been orbiting in silence and a species that has been asking questions long enough to build instruments capable of listening. The outer solar system is not empty, and it is full of messages. We are only beginning to learn to read them. For most of human history, the solar system was small. Ptolemy's solar system was Earth-centered and extended to Saturn. Copernicus expanded it to include the correct orbits of the known planets, but still imagined a bounded sphere of fixed stars just beyond. Even after the telescope revealed new planets, Uranus in 1781 and Neptune in 1846, the mental model of the solar system remained compact, a region of influence extending perhaps to 30 astronomical units, surrounded by the infinite void. The first Kuiper belt object discovered beyond Pluto in 1992 began the revision. Sedna's discovery in 2003 dramatically extended the scale. The realization that the Oort cloud extends to perhaps 50,000 astronomical units, a significant fraction of the way to the nearest star, had completed a revolution in the perceived scale of our own system. The solar system is not small. It is an enormous, complex, partially explored region of space, whose full extent and inventory are still being determined. The current best estimate for the total number of objects larger than 100 kilometers in the Kuiper belt and scattered disk is approximately 100,000. The number of objects larger than 1 kilometer in those regions is estimated at perhaps 10 billion. The Oort cloud, if it exists as modeled, may contain trillions of cometary bodies. And beyond the Oort cloud, in the space between the Sun and the nearest star, there may be free-floating objects, rogue planets captured by the Sun's gravity long ago, whose existence we cannot currently confirm or deny. This is the solar system we actually inhabit, and not the neat diagram with 8 planets on concentric circles. A vast, mostly unexplored, dynamically complex region of space whose edges merge into the interstellar medium without a sharp boundary, populated by bodies ranging from microscopic dust grains to potential undiscovered planets, all of them carrying chemical records of the events that shaped them, most of them never observed, many of them never detectable with current instruments. The Planet 9 debate is a debate about whether one specific additional body exists in this vast region. The answer to that question matters for planetary science, for models of solar system formation, for understanding how solar systems in general are shaped by their dynamical histories. But the answer to the Planet 9 question, whatever it turns out to be, is not the end of the exploration. It is a data point in a much larger investigation that will occupy planetary scientists for generations. The first systematic chemical library of Kuiper Belt objects being built now by the Architects program with Webb will be complete in a few years. The Vera Rubin Observatory's 10-year survey will triple or quadruple the known ETNO population. The Roman Space Telescope will extend infrared survey capabilities in ways that complement both. And Webb will keep reading, keep pointing, keep decoding the messages preserved on frozen surfaces at the edge of our solar system. Every message it reads tells us something about where we came from. The solar system formed from a disk of gas and dust that contained the raw materials for every planet, every asteroid, every comet, every Kuiper Belt object, and every human being. As the chemical record preserved in the outer solar system is a record of that formation, frozen in place and accessible to instruments sensitive enough to read it. Ophi carried a specific chapter of that record on its surface, written 1,000 years ago by an impact that cracked it open, and Webb found it. That is not coincidence. That is the accumulation of centuries of scientific work, the building of instrument after instrument of increasing power, the training of generations of researchers in techniques of increasing sophistication, the steady, patient asking of questions that seemed, at the time they were asked, too hard to answer. The questions about what lies beyond Neptune, about what the outer solar system is made of, about whether undiscovered planets orbit in the dark at hundreds of astronomical units from the Sun, have been asked for decades. The tools to begin answering them have arrived now, in this decade, with this combination of instruments. Hold the rock again. Feel its weight. Consider what it is, an aggregate of silicates and metals, assembled by gravity 4.5 billion years ago, from the same disk of gas and dust that assembled Ophi, assembled Neptune, assembled the Sun itself. The rock in your hand and the frozen world 90 astronomical units away are made of the same stuff, born in the same formation event, separated by the contingencies of where they ended up in the solar system's gravitational sorting. Ophi went to the outer solar system. Your rock stayed in the inner. The difference in their histories is almost entirely a matter of where they happened to be when Neptune migrated. A random orbital parameter, a slightly different initial position in the disk, and the chemistry preserved on Ophi's surface would have ended up somewhere in the terrestrial planet region, rather than in the scattered disk. The contingency is total. The physics is deterministic. The outcome looks, from the perspective of any given object, like fortune. In 2025, the James Webb Space Telescope read the chemical message on the surface of that frozen world. The message was 1,000 years old, in the sense that an impact event 1,000 years ago exposed the chemistry underneath the processed surface layer. The chemistry itself was 4.5 billion years old. The journey of the photons that carried that chemistry from Ophi's surface to Webb's mirror took 12.5 hours at the speed of light. The journey of the information from Webb's detectors to the scientists who interpreted it took seconds. The journey from that interpretation to a clear understanding of the outer solar system will take another decade, at least. This is the pace of discovery at the frontier. Not fast, not slow, the pace of careful work done by careful people with extraordinary instruments. The outer solar system is an archive. Webb is a reader. And the archive is larger, richer, and more complex than anyone knew before we built an instrument sensitive enough to open it. Somewhere in the dark beyond Neptune, at distances where sunlight arrives as a dim glow barely distinguishable from the light of nearby stars, objects orbit that we have never seen, carrying chemical records that we have never read, histories that would, if we could access them, rewrite chapters of our understanding of the solar system's formation. Some of them may have been perturbed into their current orbits by a planet we have not yet detected. Some of them may have formed around other stars and been captured by the sun's gravity billions of years ago. Some of them are large enough to be considered planets by any reasonable definition, sitting in the outer dark, unknown. We are looking. The instruments are pointed. The archive is being opened. What it will say is a question that only the next decade of observations can answer. The answer will be worth waiting for. The solar system has been orbiting for 4.5 billion years. We have been asking questions about its edges for decades. The tools to answer those questions arrived in this decade, and the answers are coming now. One frozen message at a time. If this moved you, there is more to find. The next object is already in the data, waiting to be seen. There is something this investigation has been circling without landing on directly, and it deserves its own space before the final word is said. The story of Ophi and the James Webb Space Telescope and the Planet 9 hypothesis is, at one level, a story about a specific object in a specific orbit with a specific surface chemistry. At another level, it is a story about what it means for a species to understand the system it lives in, and how that understanding changes across time in ways that are not linear, not predictable, and not finished. When the first astronomers mapped the planets with naked eyes, they knew roughly where everything was but had no idea what anything was made of. When the telescope arrived, they could see the shapes of planets but still had no chemical knowledge. When spectroscopy arrived in the 19th century, the chemical composition of distant objects became accessible for the first time, and the universe went from a landscape of shapes to a landscape of materials. When space probes began visiting the planets in the 1960s, the distant became tactile, the measured became photographed, the spectra became surfaces you could almost touch through the images. And now, with Webb, the surfaces of objects at distances that no probe can reach for decades are being read in chemical detail that was unimaginable even 15 years ago. Each step in this progression has produced surprises. The spectra of stars revealed that the sun is mostly hydrogen and helium, while the visit to Mars revealed a world both more and less Earth-like than anyone had imagined. The flyby of Pluto revealed a world of extraordinary geological complexity that no one expected of a small, cold body at the edge of the solar system. And the spectroscopic characterization of Ophi has revealed that the outer solar system carries a chemical record of its formation history accessible to instruments we built and launched and pointed at exactly the right object at exactly the right moment to read it. The surprises are not accidents. They are the predictable result of building instruments sensitive enough to see what was always there but not previously visible. The surprises tell us each time that our models were incomplete, that the universe is richer than we knew, that the frontier retreats but does not disappear. It simply moves. Each question answered opens space for more refined questions, and the refined questions require more sensitive instruments to answer, and the more sensitive instruments produce more surprises. This is the engine of science, not the accumulation of confirmations, but the production of productive surprises. Ophi is a productive surprise. Its orbit was not predicted. Its surface chemistry was not anticipated. Its implications for solar system formation are still being worked out. And somewhere in the implications that are still being worked out, questions are forming that will drive the next generation of observations, the next round of instrument proposals, the next decade of outer solar system research. There is a moment in the history of the solar system that no instrument will ever directly observe. It is the moment, roughly 4.568 billion years ago, when the sun ignited, when the nuclear fusion reactions at its core first ignited and the light pressure they produced began pushing outward against the infalling material of the collapsing molecular cloud, clearing the inner regions of gas and leaving behind the solid and liquid materials that would eventually form the planets. This moment is called the T Tauri phase. The Sun was a T Tauri star for the first few million years of its existence, a violently active young star blasting its surrounding disk with intense radiation and particle winds. The chemistry of the early solar system was set in large part by the conditions during this period, the temperature gradients established by the young sun's radiation, the distribution of volatile and refractory materials at different distances, and the specific composition of the molecular cloud from which the sun formed. We know these conditions indirectly through three main data sources: the compositions of primitive meteorites, the chondrites, which are fragments of asteroidal bodies that never melted and therefore preserve the mineral assemblages that form directly from the solar nebula; the isotopic ratios of various elements in solar system materials, which record the nuclear history of the molecular cloud and the specific mix of stellar material that contributed to it; and the compositions of the most primitive comets and Kuiper belt objects, which formed in the outer disk where conditions were different and where some of the most volatile materials were preserved. The Webb observations of outer solar system objects like Ophi are adding a fourth data source into the spectroscopic characterization of intact bodies in the outer solar system. Bodies large enough to have preserved their primordial chemistry without significant geological alteration provides a window into the composition of the outer disk at the time of formation. The specific compounds present and absent, the ratios between different molecular species, the distribution of carbon and nitrogen and oxygen in organic compounds. All of these carry information about the molecular cloud composition, the radiation environment at specific distances from the young sun, and the temperature structure of the protoplanetary disk. The chemical record on Ophi's surface, the compounds exposed by the impact event, are not this pristine. They represent interior material that has been processed by Ophi's own geological and thermal history, which for a 430-mile body means some degree of internal heating from radioactive decay in the early solar system. But they are closer to pristine than surface material that has been processed by 4 billion years of cosmic rays, and the comparison between the surface spectrum and the impact-exposed spectrum gives scientists a measurement of how much modification the surface has undergone relative to the interior. That comparison is itself scientifically valuable. It calibrates the cosmic ray processing models in a way that laboratory experiments cannot fully duplicate, because laboratory experiments cannot replicate the specific radiation environment of the outer solar system over billion-year timescales. Every well-characterized outer solar system object Webb observes adds to this calibration, and improving the models that are then applied to every subsequent observation. This is the infrastructure of science, each measurement improving the tools that make the next measurement more precise. Ophi does not solve the formation history problem in isolation. It is one data point in a growing library. But the library did not exist before Webb. The first entries in that library are being written now. There are 4 objects in the outer solar system whose significance to the current investigation is particular, whose properties collectively define the question space that Webb, Vera Rubin, and Roman are being tasked to explore. The first is Pluto. Pluto is the most studied Kuiper belt object and the only one visited by a spacecraft. The New Horizons flyby revealed a world of extraordinary complexity: nitrogen ice plains actively convecting due to heat from below, mountain ranges of water ice kilometers high, a thin but dynamic atmosphere, evidence of past geological activity. Pluto is not a static frozen ball. It is a geologically active world whose surface changes on timescales relevant to human observation. This was not anticipated. It changed the expectations for every other Kuiper belt object. The second is Arrokoth. Arrokoth is the most distant and most primitive object ever examined by a spacecraft. It is a contact binary, 2 lobes of ancient material merged at low velocity, its shape and composition largely unchanged since accretion 4.5 billion years ago. The New Horizons flyby of Arrokoth in 2019 provided the first close look at a primitive Kuiper belt object formed in place in the cold classical belt, without significant scattering or dynamical excitation. Its composition a homogeneous dark reddish material consistent with processed organics, confirm the basic spectroscopic picture developed from ground-based and space-based telescope observations. The third is Sedna. Sedna's orbit is so extreme, its perihelion at 76 astronomical units and its aphelion at roughly 1,000 astronomical units, that it occupies a dynamical regime no other well-characterized object shares. It is not a scattered disk object, because its orbit does not interact with Neptune. It is not a classical Kuiper belt object, it is something else, an outlier, and a member of a population that should exist but whose other members have not yet been found. The inner Oort cloud object that everyone expected to coexist with Sedna 2012 VP113 was found in 2014, but the population as a whole remains undiscovered and its full properties unmeasured. The fourth is Eris. Eris is larger than Pluto in mass, similar in size, and sits in the scattered disk at a current distance of about 96 astronomical units. Its surface, unlike the reddish surfaces of most Kuiper belt objects, is highly reflective white, covered in fresh methane ice that is thought to be continuously renewed by a cycle of sublimation and recondensation as Eris moves through its eccentric orbit. The contrast with Pluto's darker, yet more reddish surface illustrates the diversity of outer solar system body compositions and the range of geological and compositional processes that produce them. These four objects define a space. Pluto shows what geology and atmospheric processes do to a Kuiper belt body large enough to have internal heat. Erekos shows what the most primitive, unprocessed Kuiper belt surface looks like. Sedna points to the population in the inner Oort cloud that remains unmapped. Eris shows that compositional diversity in the outer solar system is not well captured by any simple model. Ophi sits in the scattered disk, dynamically related to Eris and to Sedna, but compositionally distinct from both. Its Webb-characterized surface places it in a specific part of the compositional space that is consistent with a specific formation history. Imagine that formation history, when placed in context with the dynamical picture of Neptune's migration, provides a constraint on when and how the scattering of the primordial Kuiper belt occurred that previous observations have been unable to supply. This is the scientific value of Ophi, stated precisely. Not the discovery itself, not the spectacular orbit, not the dramatic headline. The chemical constraint on Neptune's migration history that no other currently available object provides as directly. One constraint among many that will be needed before the full picture comes into focus, but a constraint that was not available before Webb read the message on Ophi's surface. The honest accounting of the outer solar system in 2025 must include an inventory of ignorance alongside the inventory of knowledge. Now, the two inventories are in some ways more balanced than the popular presentation of science typically acknowledges. We do not know whether Planet 9 exists. This is not a matter of insufficient search effort, but of genuinely insufficient data. The surveys that have been conducted cannot rule out a body at the predicted parameters. More sensitive and more comprehensive surveys are needed before the null result becomes meaningful at the required confidence level. We do not know the full extent of the Oort cloud or what it contains. Theoretical models predict its existence and its broad properties with some confidence, but direct observational evidence for the Oort cloud exists only in the form of long-period comets arriving in the inner solar system, and those arrivals sample only a tiny fraction of the cloud's population. The total mass of the Oort cloud, the number of objects it contains, its spatial distribution, all of these are estimates based on dynamical models calibrated against the thin trickle of long-period comets we observe. We do not know how many planet-sized bodies exist in the outer solar system, detached from Neptune's influence, orbiting at extreme distances. Sedna is almost certainly not unique. The question of whether there are dozens of Sedna-like objects, or hundreds, or none at comparable distances, is currently unanswerable. We do not know the composition of most Kuiper belt objects. The Architects program is building the first systematic Webb-based chemical library, but it targets a specific sample selected for scientific interest. The broader population remains uncharacterized at the spectroscopic detail that Webb can provide, as mapping the full compositional diversity of the Kuiper belt will require years of observations and a much larger sample. We do not know the interior structure of any outer solar system body except Pluto. And even for Pluto, the interior knowledge is largely inferred from surface observations rather than directly measured. Whether Ophi has a differentiated interior, a rocky core and icy mantle, or is compositionally homogeneous throughout, is an inference from its size and estimated density, not a measurement. A direct measurement would require a spacecraft mission or detections of a moon, from whose orbital properties the central body's density can be derived. We do not know whether the composition of the inner Oort cloud, the region where Ophi's orbit reaches at aphelion, is distinct from the Kuiper belt and scattered disk, or whether it is a smooth continuation of the same population. Models predict a compositional gradient based on formation distance, but the models are poorly constrained at these extreme distances. This list is not meant to discourage. It is meant to communicate the scale of the open investigation. The outer solar system is the most accessible example of the kind of profound ignorance that characterizes the frontier of any scientific field. It is not a solved problem wrapped in mystery. It is a genuinely incomplete picture, with the most important elements still missing, being assembled piece by piece as instruments improve and surveys deepen. The honest scientists working on this problem know this better than anyone. They know their own results' limitations, and they know which parts of their models are well constrained and which are placeholders that will need to be replaced when better data arrives. They hold their conclusions, as good scientists must, with calibrated uncertainty, confident about the things the data supports strongly, and reserved about the things it supports only marginally. Ophi's Webb characterization is strongly supported. The anomalous compounds are real. The formation inference is less strongly supported and carries explicit uncertainties in the published papers. The implication for Planet 9 is not directly supported by the surface chemistry data, and is appropriately left as a dynamical question to be addressed by orbital analysis. These are the distinctions that matter, and they get lost in any presentation that reduces the story to its headline. The headline is real, a 1,000-year-old message on a distant world, written by an impact and read by Webb, speaking to the early solar system's history. Every word in that description is accurate. The message is real. The age is real in the technical sense the investigation described. The distance is real. The content is real. But the meaning of the message, its full implications for the Planet 9 question, and for solar system formation models, is still being worked out by the people whose job it is to do that work carefully, and without the pressure of producing a narrative that resolves before the science does.